Okay, can you see my screen?
Yes.
I can't see my mouse.
I don't know if we see your mouse or my mouse. No, we see my mouse and not your mouse. Yeah, now we see your mouse somewhere. Yeah.
Okay, so right, can you see the screen now? Okay,
Yeah.
so hi everyone. I have to in the beginning apologize for the last few slides. I was making them in the airplane, so they're just screenshots of the paper, but just the second half of it. So the paper that I'm presenting today is called Learning Dynamic Graph Representation of Brain Connectome with Spatio-Temporal Attention, which was published in NeurIPS 2021. To give an overview of the paper, they are working with brain data, fMRI data, and they want to get a graph representation of the brain connectome, but with the difference that they want to take advantage of the dynamic functional connectivity of the brain, which is a new thing. They have also in the past, some other papers have tried to do that, but they either are not using the dynamic representation of it, or if they are reporting less accuracy than if they were not using it. And their method is called STAGIN, STAGIN, whatever you pronounce it. And so they started by saying how graph neural network, the rise in their research is helping this research field because that's the type of data that we work on with the graph. And yeah, here she's just saying, as I said before, that they, other papers have tried to incorporate dynamic functional connectivity, but they either were reporting less accuracy and also their methods doesn't have a full explainability of this paper. So this was not part of the paper. It was just for me because I wanted to also, it was also needed to be. So I went ahead and did a little reading on the internet about graph neural networks. So the slides from 5 to 21 are from that website. That is just the basic explanation of how graph neural networks work. So graph neural networks is a type of deep learning models that work with graph structures and works with the relationship between entities. And you basically have, so you have three different things to keep track of. There are the vertices, the edges, and the whole global graph thing. And so you have a different embedding for each of them in the graph. And the reason that graph neural networks are being researched a lot more in the recent is because they have a special characteristics, like they're good with dealing with heterogeneous data. For example, like a lot of research in chemistry uses them for molecule formulation and 3D structure. Lots of social network research is using graph neural networks. So in this context, there is three different types of tasks that we want to do. First task is the whole, to predict the property of an entire graph. For example, if you want to see if a molecule has an odor or not as a whole, as a whole graph, or if it has rings or so. So that's the big picture. It's sort of like image classification. which associates one label to the entire data. Another part is node level task, which predicts the role of each node. This is in analogy like image segmentation, which you segment each pixel in an image and assign it to an object. And lastly, it's the edge level prediction, which is identifying the role of each node in connection with other nodes. If we want to make an analogy for it, is sort of like scene understanding, where you, as you see in this picture, you are trying to understand the relationship between different objects that we have extracted before. So there are some challenges when we want to work with graph data in machine learning. One of them is that how do we present them? How do we represent them in computer? So if we want to use JSON metrics, there are two problems. First of all, because in many examples, like in social network examples, the number of nodes could be in millions, and the number of edges are also a lot, but not that much. So the JSON metrics that we got eventually will be very sparse, so it will be very time consuming and inefficient to work with matrices. And also in graphs, if we work with adjacency matrices, they're not permutation invariant. For example, this simple loop graph here can be represented with 24 different adjacency matrices, as you can see here. So one way to address that is that they use adjacency lists that lists all the edges in the graph instead of the adjacency matrix, and that will be permutation invariant. So let's start with the simplest kind of graph neural networks. So graph neural networks uses different separate MLPs for each of these components. So one for the entire graph, one for the set of vertices, and one for set of the edges. And so one layer in a simplest graph neural network is like this. You have the graph, you would apply some MLP or any kind of differentiable function on them, and then you'll get the same graph with the same connection, but the embeddings have changed and updated. So you can stack multiple layers like this and get more complicated embeddings for the graph. But as we know from the convolutional neural networks, that pooling is where the information is being spreaded, like different parts are being connected together, and that's a very important layer in that. So we want to have pooling in graph neural network as well. So what happens here is called aggregation, where for each, so it can be aggregated at an edge level or node level. For here in this example, I'm showing a node level where we have an embedding for the node itself, which is the top one, the top like the red columns. Let's suppose that's the information vector that we have for the node. Then we have two edges that are connected to this node, and they have their embedding vectors, and we aggregate them in one embedding. And usually this aggregation operation is summation. So, and we show it here as a pooling of edges to vertices. So that's what we are doing here. So then after we had the pooling phase, and we can apply another final classification for our desired task, if it's node classification or edge classification. So if it's edge classification, actually the pooling will be in the other direction. The pooling will be from vertices to edges. And all of this is very well explained in the link that I had in the website. So, and it has like graphics, and I really encourage to look for it if you are not familiar with this. It was very helpful for me. So here, as I said, if you want to do edge prediction binary classification, you do the pooling in the other direction from vertices to edges. So with the pooling operation, this is what end-to-end graph network models at a simplest form looks like. We have the input graph. We have several GNN blocks that keep the same kind of the structure of the graph, but it updates the embeddings and makes them more complicated, makes them include information from neighboring nodes. So basically, for example, when you have 3 graph neural network layers, every node has information from all of its neighbors up to 3 connection. If you have more layers, it will be more and more complicated, and you'll have access to information further away. So in general, yeah, so we have in the graph neural, there are 3 steps that it takes. The first step is gathering the information, which is, for example, node is you concatenate all the information you have about that node, then you aggregate it with the neighbors, and you do a combination from all the nodes to get a final presentation. And just after this function after the summation is the combination part of it, and usually this is MLP network, but it could be any other function. So that was the part from the website. This is now from the paper. So, as I said before, we have the aggregate function and we have the combine function. And the choice for these 2 functions, the aggregate and combine, which in the example that I showed was summation and MLP, is defines different variations of graph neural networks that there exist. There are many, and they basically come down to these 2. So here, this graph isomorphic networks is using summation as aggregate and then 2-layer MLP as a combine. And so they formulated that exact thing. So if you replace the aggregate function and combine function in one formula and replace them with summation and MLP, you'll get the top formula, and you can rewrite that in the matrix form as below. Then you have the readout function, which takes the updated node features and computes one representation for the whole graph. So in this case, for the graph isomorphic networks, this readout function is just an average, a sum and average divided by the number of the nodes. Where so they explain how this phi mean function, this readout function, basically a decoder. If we want to make it analogy to convolutional network. It works like a decoder. And so they have, in this proposition, they say that this function, this phi mean function, works as a decoder, and because it's constant, it works as like a fixed constant base. And they prove their proposition here. And the problem with that is that if you have a fixed basis, so let's say that you have two features, H1 and H2, there's only one representation that you can get for that. And so you won't have really a lot of freedom here. But if you apply, instead of using an average readout function, you use an attention-based readout, which uses weighted sum of them, you assign weight to them. Instead of getting only that point, HG, you can have access to the whole area in that rectangle, and that will give you much richer representations of the graph as shown here. And later we'll get to this, but so they also have a loss function that encourages orthogonality, because based on this geometric explanation, they want to maximize this area where we have the freedom, or that to construct a representation from basis. All right, so this is where it gets to the screenshots. Sorry about all the text, but here they are explaining how they get the graphs. So they're getting the graphs from 4D fMRI data, and they map this to certain predefined atlas of the brain that we have to extract regions, and based on the regions and the so the threshold, the top 30 percentile of the connections between these regions to get one final graph representation. This graph will be undirected because it's just a correlation. And they use this 30% here as a hyperparameter, but later in the appendix, they show that this is not very sensitive to this number. It can actually get better performance if they increase it to 40. So this is a figure to explain how they get the graph. So they use a sliding window on this matrix of regions of interest versus time matrix. And so they get the dynamic graph representation. What they do here, which they show that's very helpful, is that on top of the, was there a question?
There was an earlier question from Ibrahim, but I don't know if Ibrahim, you want to ask it? Or
yeah,
you?
just from the previous slide, yeah, about the combine, how they combine the, is it concatenation mainly?
This slide or the previous slides?
Previous slide, yeah.
This slide.
I forgot the number. There is a term combined, right? Read
okay.
So yeah.
So their method is called a spatio-temporal graph isomorphic network. So they're I'll get to exactly that, but so they're based on graph isomorphic networks, which use a two-layer MLP as the combine and the summation as aggregate function. But their readout function is different. They use attention in the readout function.
So how they combine?
Combine.
Yeah, like you have a word combined there. I think that's what Ibrahim was asking. So,
Oh,
here's
So
20-second slide, right?
so you have so this this step here is called aggregate, where you aggregate information from edges to
okay.
then you combine this summation for all of the nodes, and you
Always
get
coming.
all. So there are
I think-
five nodes in the graph. You compute
Okay.
what's being shown here for all of them. Then you will have 5 different vectors, and you use in this setting, you use a two-layer MLP to get from that those 5 vectors to another new vector, which is this process called combine.
Do you concatenate those vectors or you add them before passing it to the MLP?
Okay, so let's see what they do here. I think seems like they added.
It seems like, I mean, this is kind of like a general, I'm gonna say it's kind of like a general observation about like different machine learning algorithms, but like if you think of like spam detection and like bag of words approach to treating like an email with like a bag of words, there's like you could rearrange all of the text and there would be like no like that document would still be considered the same. And there's like many different documents that would be considered the same. And like with the summation and the graph neural networks, it's like there's a bunch of different neighborhoods that would all be considered the same. So it's like how you define this aggregation loses information and treats a whole family of graph configurations as being identical. And it seems, and that can be really useful in like classification. But if you're like if you're doing what I'm doing, which is like service reconstruction, if you're treating like certain categories as being the same when they're actually different, then or you need that information, and that aggregation function would not be good. So like kind of just going back to what Sajad said at the beginning, it's like sometimes the pooling operation happens on like vertices or edges or whatever. It's like the whole thing that matters is like what you consider equivalent families of graphs, and the architecture will define that, and the usefulness of the neural network will be contingent upon how well you define that for your company. But anyway, that's just something I wanted to throw out.
So this is their method. I think that's what.
Yeah. I saw a line there, right? The stack of the feature or stack of the node after aggregation, like this, maybe in the upper page, the previous page.
It was
the previous page, yeah, page. Oh, I see. No, maybe more.
Yeah.
This one is here is the stack of node feature vector.
Yes.
Does it
So
mean,
yeah, I think
aggregate and combine like this?
I think they concatenate these vectors
like
into
this.
one matrix.
Yeah, that's
H.
why. Okay.
Yeah, okay. Yeah,
Okay,
thank you for that.
No, but that's not concatenation. It's a weighted average.
What average?
Look, you put them into a matrix, but then you multiply by W. You're recombining them, like you're mixing them. What is it? It's also a adjacency matrix between node features. So yeah, this is just a linear algebra way to express message passing. This is not what you're asking. This is
No.
the message passing part.
Okay. Mhm.
See, it's like it's how they remix, how they add it together through the weights.
Hmm.
It's the previous process before the MLB. It's you're getting the same number of vectors as you started with, but such that the neighboring nodes in the graph got aggregated.
I think what you are asking describes the readout function, that you have the stack of all these vectors and you apply this mean pooling, the pooling vector, and get one.
So this is just the average. Yeah.
What?
This is average, 1/n. This is just
Yeah.
the average.
Yeah, so that's the way they do it in the graph isomorphic networks. They use basically just average for that.
Yeah. Okay. Thank you.
It's interesting how let me just like a small rant on that. It's kind of another proof that we humans have complexity bias. Talking about deep sets versus MLP. We had a conversation in the previous meeting. Highway networks happened first, and then like in May, Schmidt-Huber's group puts highway networks online. And then in December, Microsoft puts ResNets, which is like, oh, we can simplify, totally remove the gating and just make the skip connection not adjustable. Then this graph neural networks remind me of multidimensional STMs. Multidimensional STMs are doing the same, but only in a very, very smart way. They're not only talking to your direct neighbors. They're looking at the entire graph for each node and deciding what matters, how much far back from you. So like that came first. That is like an overcomplicated method. Message passing existed long ago, but not for the neural network part. And then somebody saw, oh, well, I guess maybe they didn't see the connection. Maybe they saw the connection, like multidimensional STM can just simplify and only do the immediate neighbors. So Markov order 1, forget about all the history before that we put through. So that's interesting. We start transformer, much simpler model than LSTM. LSTM is just like so complicated, and we didn't think about transformer 20 years after LSTM.
LSTM comes from models of the way. LSTM is just a model where it literally comes from like.
Well, there's long-term, like
that idea of recurrent networks is that if you have neurons and then the connection matrix of neurons, right?
Well, I'm not talking about recurrent.
I think when we came to that first, because they came from computational neuroscience, came recurrent neural networks, then people adapted that to work better, like straightforward the LSTM.
No, but like RNN is okay. It's kind of a simple model, right? It's fine. But then the LSTM is just like so many parts and like everything like this Swiss Army knife. But then you go to transformer, the self-attach. Oh, it's so simple. Why didn't they think about it? It's kind of we go reverse. Like we go from
computational like I think a lot of ideas came from neuroscience, and then now we're seeing more of this like engineering approach, where it's like who cares? Which I don't think per se is good. Yeah.
Well, it's still going from complex to simple. It's kind of weird. Like, why don't we go from simple to complex? Well, anyways, go ahead, Sajad. Sorry.
Okay. So I think we were here. So anyway, one thing that they did in this paper that was different and they showed it was very helpful was that they added an encoding of timestamp to every node and every edge so that they also preserve the information about where the time is at this time, and then they apply a one linear set of weights, or like a one layer MLB, to get the final vector. You know, as you can see here, there's the one hot encoding vector, and they concatenate it with the timestamp, and they also they said here what the timestamp function is exactly. It is gated recurrent units. So this is how they compute the X. They concatenate the timestamp with the one hot encoding, and then they apply set of weights to get that. So this is the main figure of the paper, where they have the whole thing summarized. So as the input, you have the matrix that I showed here, which is the time versus the regions of interest. And you apply graph isomorphic networks on it with the attention-based readout function. So in the original GIN, the readout function is that just averaging function. But here, this J row and C row, these two things that it's the contribution of this paper, you can see on the right side. These are attention-based readout function, which we'll go into later. Then when they get the sequence of spatially attended representations, they apply a transformer to get the sequence of time temporally attended representations, and they do one average at the end of it. So there's like the first spatial, then they're first spatially attended, then temporally attended, then they get the average of that, and they assume that, or they show that this is the representation for the dynamic graph that is changing over time. And you can see on the right how these two different attention-based readout function works. Yeah, this is just what I said, where they were they're finding reasons to why we need attention here, as I showed in that picture before. Instead of being able to only construct one point with two bases, we want to be able to have the freedom to choose any point in that space. So that's how attention is helping here. And there are two methods, this GARO and SERO. So for this one, they used key query embedding based on transformers. And you can see it here in the figure as well. They average these embeddings, then they apply the transformer and get the representation. Any questions?
I have some comments. So why this is interesting is because they are learning the graph. Most, if not every, GNN paper works that already exists, and like some other procedure is using the graph. And then there was a large field before deep learning. You people probably missed that. It was about community detection and graphs, small worldness, etc., etc. It's like the like huge in neuroscience. People were talking about the network analysis that was called, but then the network came from somewhere else, and somewhere else was usually correlation checks with the threshold, which is that seems weak. And here GNN is kind of repeating this whole GNN field is kind of, in my view, repeating this path of starting with a graph that exists already, given somewhere for you, and then work on an existing graph, do some analysis, and then 5 years later be replaced by another IP. But this was a joke, just for the record. But if you learn the graph as well, that is interesting, and that we stumbled on that paper for a few reasons. One of them is that Usman used it in his work as a baseline, and you can even use the authors every communicates it, but it learns the graph.
But what do you mean by this paper learning the graph? I guess all the neural networks, the graph neural networks, they do work on learning all the embeddings and vectors within the graph and then giving you some.
Within the graph, but the graph is given. The graph
Not exactly. Like, for example, I was working on this project for protein synthesis affinity power, where the graph is not given. You have to create the graph from the data that you have and then learn from that.
Yeah, how do you create the graph?
I mean, you already have the, you have the vectors from that, you have to create the graph.
How do you create it? By correlating the graph and then applying GNN.
No, the GNNs are, well, I'm creating the network itself, that is the GNN, not creating the graph.
So you're using a fully connected graph,
And
like everything to everything, because you want to do
everything
message
to
pricing.
everything cannot happen, right? Because you have like different edges and different connections for that.
Where do you take the edges from?
So the edges will be basically from the, that has to come from the previous embedding that we already have.
Yeah.
So
So that's my point. And here they're learning the graph. So, the result is the graph, and the also time change. Also time change. GNN operates on a graph. And by graph, I mean the abstract data structure or abstracting nodes and edges between them. This is a graph. Forget about the embeddings and stuff. This is metadata on top of it. So this edges, the connection, the sparse structure is usually in the GNNs is given from something else, a previous process. That's what I mean.
also the output of this.
Output of this is a set of graphs of connection. Yeah, but they're using whatever data, but yeah, the brain, the fMRI.
But the kind of have like ROI structures, the way kind of thing. No,
ROI structure, but not the connections.
no, I understand, but they for each ROI, it's like basically embedding, then it's like kind of learnable embedding in some sense.
You have 100 ROIs, so you have 10,000 possible connections.
So the big sign window of the ROI times that. So the giving is the number of nodes for it, and then we have embedding.
This is not a graph.
I know, but like it's in the sense that it's a computed graph on a learnable embedding system.
They're learning the graph. Yeah.
Yeah, like it's just like additional features.
Or estimating, they like estimate.
So basically, instead of like in this case where like they construct graph from raw features.
Those are raw features.
No. Like in this case, like the graph constructed on raw features. Here the computer embedding first, and then the graph constructed on embedding. But to do that, they already have kind of prior knowledge. They have ROIs, right? They already kind of.
The nodes are defined, but the graph is not defined.
Yes, but like they already kind of like they can't define it on embedding level, but it's kind of learnable and embedding. So in the sense, in his
I
case,
think our definitions of what a graph is diverge here. Even when you know nodes, temperature, height, width, weight, those are the nodes. Are the variables.
I understand,
But you don't know
like,
the
it's the
connection.
same. Like, it's the same. You compute adjacency ranges.
Yeah, I mean, that's, I mean, you effectively.
No, exactly. You compute them, and this is learning.
But this is also like, it just future instructions that you learn basing from the model. It's just another level of like,
I mean, you used to doing.
No, it's unreal. It's a graph. They're learning a graph, and a graph consists of edges.
but it's the same thing. They just add this learnable embedding before building the graph. That's all. You can build graph from raw data, but say you build graph like by learning embedding first.
But their graph is built by the network. It's not built by correlation
I
matrix.
understand, but I'm saying the layers builds
Yeah, that's what I call learning. They learn the graph.
but
It's not hard coded, and in the
it's
other cases,
hard-coded
hard
because
coded.
it's hard-coded because they improvise.
No, the nodes are not the graph. Graph is two sets. So they give one set, but they learn the other set.
But I'm saying that, example, if you give nodes like otherwise, this corresponding time series, and then we compute embedding. And then
Of
even
each node, you still don't have a graph.
I know, but then like layer does it.
No.
So I'm saying that if the method takes, so giving to the method only the,
No, we're giving the data, but B is implicit in the data.
yes, but the methods that like, example, I'll say M, transformation method, is basically kind of computing this adjacency in some sense, right?
Yeah, learning adjacency.
Yeah, but like it still comes from here, no?
You can specifically learn a similar thing.
I mean, computing adjacency, like simple way by computing relation, it's just simple way already.
You could make all your embedding so similar that it's going to graph, or you're going to keep it not so.
If you're using correlation.
But whatever similarity.
Yeah.
But it will learn that, right? Like it will learn to use that similarity to create a graph. Like if the embedding.
It learns a graph. I'm not claiming anything else. It learns a graph. It learns which graph is useful.
I don't think in this case they use like vector and adjacencies.
Yeah.
Yeah, but you need adjacency. For GNN to work, you need the adjacency.
You can learn that adjacency.
Hmm?
You can learn that adjacency.
Yeah, that's the point. They learn the adjacency.
Yeah, but they have strong prior not less.
Yeah, you have to have models.
But it's kind of already comes like not like from raw data. Like raw data will be just also and series, and then you might use like spectral plot in like you already. This is already like something more than because rights are not that relevant, it's prior knowledge, and you can have different rights.
Yeah, but still, it doesn't. I don't know who you argue with.
No, I'm just saying.
My statement is still.
This is not
Operate on it.
It says this is not novel design contribution,
It is a contribution.
but it's not novel.
Who's done it before?
Because as in like they're using the graph players that already been done.
Graph players don't learn a graph; they just operate on it. Adjacency matrix, as I always said, is learned, can be learned. So they learn adjacency. And so the trick there is that when you start learning adjacency matrix from the data, your adjacency matrix becomes path dependent.
So,
You can make it
let's take simple graph attention. Attention weights is basically adjacency matrix.
Attention weights is basically adjacency matrix. Yeah, okay, you can, but you have to learn that.
Yeah, you know, but I'm just saying that this paper doesn't cater it, it's catered by people who develop graph neural
You already learn parameters for, and then you're doing some of the something. But it's not like you're learning. It's not like you're making a graph while you're learning. I mean, that's.
It is like you're making the graph while you learn. That's the point of this thing.
No, I'm just saying the claims that
they specifically like developed the graph. I think it's not true that they did it. It's done by the layers. But layers already was before.
Yeah, but like if you take convolutional GNN, it operates on a given graph. If you take the message passing, the LSTM like GNN, it operates on a given graph already. And so you're saying, okay, there is a continuous version that it's fully connected, but it's weighted by the attention matrix for each of them.
Yes.
So it's kind of, but it's still fully connected graph. We need a threshold, we need a discrete graph. So I don't know, like, yeah, in the previous, with Sajad show, in the previous summation, you have H, you stack the H matrix, you stack all of the embeddings from all the nodes, and you multiply by W, and this W is a weighted recombination. Well, but you have an adjacency matrix there, which is discrete. So it filters out. You could have a continuous adjacent matrix there, fully connected, but you know, contribution.
Yeah, because they use Jim. I mean,
Okay, we need to continue, but yeah, so I didn't get your point. Sorry.
no, I just think the claims that say, hey, that's something no, I think it's not true because it's been done by other people. I mean, the main nodes, I think, application.
Maybe.
But I mean, even if you look at this figure, where is the graph is actually the output? It's just giving me a vector, the output vector, which is the H of G in this case. Right?
No, the graph, there was another one. The graph there in the tilted plane, and this graph changes with time.
Oh, the graph will change with respect to time. That is, I mean, that's the case of temporal information anyway. I mean, it won't. I mean, if you don't have a temporal information, then it doesn't make sense that the graph will be constant. But yeah, but where's the
This dynamic functional connectivity, dynamic FC AT is the graph.
Let's see.
The timeline at the rightmost bottom dynamic FC. Yeah. So this one is learning.
Already constructed.
No, the method is constructed. The transformer, whatever the encoder constructs them.
Not with respect to the time.
To time and data. We would take
Yeah.
from the data. Of course, they're using the same methodologies that they had before.
Right.
As transformer is also not novel, it's just simple bilinear matrix multiplication. But yeah, I don't understand it. It's a novel use of old methods like everything else.
But they still give a lot of like prime knowledge. Like Rise has already.
Yeah, they're not learning, like they're not doing ICA like analysis. They're not learning the variables. The variables are given, but they are learning the graph that connects those things.
But this is any graph now.
No, the graph neural operate on a graph as given.
You usually don't give attention, like adjust matrices input. I'm just saying that you give the nodes, but some graph neural network figure out how they connect.
But no, here is like fully connected. Graph neural network operates on a fully connected. So it's kind of
But
like
I agree, you need thresholds to find sparse. There are
yeah. So graph neural network kind of operates on either on fully connected graph or on a given graph. That's well, anyways, Sajad, can you like how far are you?
Yeah, so just
I think the talk is canceled.
Okay.
So we
okay, so I'm not sure who said that, but I kind of overheard the sound quality is very bad. But so I think someone said that we're like learning the connectivity of here. I think what they are, so they're not learning the graph that has the connection. They are acquiring that connectivity graph using all this what deterministic stuff. Not deterministic.
Are you just
not
using correlation matrix?
Yes, what they are learning is this HG dynamic, which is a representation of the graph that has all the information from the changes. So this, we have one graph at one time point, and then another time we have a different graph. The connections are different. This HG dynamic is supposed to combine all of their information, and then we use that for downstream tasks for whatever classification they have. So that's what they're learning. They're not learning any connection.
So Alex, maybe I am wrong. Maybe they're just using correlation matrix as a adjacency.
Things that might analyze the basic relations.
Yeah. Like, can you go to the previous slide, please? Just real quick. No, the one with the FC. Yeah, this one. Yeah. So look at the sentence before the formula. The FC. So they compute correlation between elements. That's it. So they're not learning the graph. Like it's something like.
I mean, they do thresholding, but this thresholding is specification approach. Like the other approaches, some people like throw Gaussian on the node, and then it kind of specify the solution, but doesn't like specify completely. So I think that this is the way how they can analyze the presentations that they don't sometimes see the steps. So, and the graph neural network just kind of combines different modes together and find the perfect rating for it. So
Yeah, graph neural network is like just a way to do parameter tying, basically. It's not anything too complicated.
it just looks like they kind of find the graph.
No, the graph is still functional connectivity. Yeah, the graph is still correlation matrix. Thresholded correlation matrix like everyone else. Not that they learn. So like at least Usman has used attention matrix as the graph. So it was learnable and changeable. Here it will kind of change the moment it will learn. So in Usman's work, the graph is the only information that passes the adjacency matrix. It's the only information that goes to classifier. It has to operate through the graph structure, not still with no composition. Here, it keeps information in the embedded instead of like encoding into the graph. It doesn't. It can. That's why maybe they're insensitive. Take 30%, take 40%, take entire connected matrix. It will be even better because you're just like using all of the information. Okay, I get the point. Okay, is there any like last words?
Yeah, no, nothing. Just they have two different ways. One is with transformers, one with MLP they attend. And just the thing is that the one with the MLP has to have the exact number of nodes, which is not always the case in graph representation, but in brain data, because we have the atlas is applicable. And this is the orthogonality regularization that I talked about. They encourage orthogonality between these H matrices to maximize the expressivity of the model, as I shown here. If you have the orthogonal, there more area to cover. And this is the results section that they found that most of some of these methods are not using the dynamic functional connectivity. So this paper is doing better than all of them. And other methods that are using dynamic functional connectivity, they are reporting actually worse results than those who are not. So this is the advantage of this work, which is uses dynamic and also have better results. And this was a data set that they had. So they used that final HG dynamic to either do the resting state task, which was the rest or not, or the task HCP task, which are just different 7 classes. And this is what one last figure they had is actually in appendix that was showing that the model is actually working, where the attention is shifting during different tasks. So, you know, if I zoom, you can see that when the task shifts, the model is changing the attention. So it is their way of showing that this is actually a dynamic representation. So like when here the task of emotion shifts from face to like shape or rest, the model attend to that in all of the layers. No, that was the last slide.
Okay, thank you. Let me stop the recording here. Thanks everyone for listening to this on YouTube.
One thing